Measuring the spread of data. That's a statistical and descriptive analysis technique which tells us how dispersed or concentrated values are around the center or mean of the dataset. It is important because averages alone don't reveal the full picture. Two datasets can have the same mean but behave completely differently. As you can see in the figure, there are three graphs. They can be corresponding to three different stores in our Rossmann dataset example. Each of them has the same mean, but they have different distributions or spreads. The one here at the top has a narrow distribution. These two at the bottom have a broad distribution. A narrow distribution means most values cluster close to the average, suggesting stability and low risk. A broad distribution indicates higher variability, signaling unpredictability and the need for closer monitoring. In the Rossmann sales dataset, for example, two stores might have the same daily average, let's say 7,500 euros. But one may fluctuate wildly, let's say from 2,000 to 15,000 euros, while the other stays between 7,000 and 8,000 euros. The first store has a broad spread, suggesting unpredictable customer flow, unpredictable sales, and potential risk. The second has a narrow spread. This indicates a stable and consistent performance, ideal for forecasting, staffing, and stock management. So, understanding the spread helps the businesses because you can assess the consistency versus volatility in the performance. You can identify outliers that may indicate risk, error, or opportunity. And you can evaluate reliability and predictability, which is crucial for planning, forecasting, and resource allocation. In order to calculate the spread of the data, we use a statistical concept called quartiles. This is how it looks like. Quartiles, as you can imagine from the word quarter, divides a dataset into four equal parts after sorting the values from lowest to highest. The first quartile represents the 25th percentile, the second is the 50th percentile, and the third is the 75th percentile. The first quartile means that 25% of the data falls below this mark. The same goes for median or the second quartile, which represents the 50th percentile, which means that 50% of the data falls below this mark. Same goes for the third quartile, which is the 75th percentile, indicating that 75% of the data falls below this mark. And then we have the 100th percentile, which is the largest value or the maximum. We calculate the interquartile range. The interquartile range is the difference between the third quartile and the first quartile, which means it is representing this gray shaded area in our graph. It measures the spread of the middle 50% of the data, ignoring the extremes. So the minimum 25% and the maximum 25% of the data is ignored. A smaller IQR, a smaller interquartile range, suggests consistency. A larger IQR indicates variability. In business, IQR is especially useful for identifying typical data patterns, in our case sales patterns, while filtering out unspoken spikes or dips. Let's see this in action on our Rossmann sales dataset. Here we have our dataset, and we want to continue analyzing our sales dataset for any outliers and calculate the overall spread of the data. But before we do that, let's clean up the data a little bit and remove those sales values which were equal to 0. We want to check only for our stores which are open right now. For this, let's make a copy of the raw data and rename it as cleaned data while removing the sales 0. Here we have our cleaned data set now. And now you have a couple of options. Our data seems sorted. So either we simply scroll down to the point where we have 0, or we could filter only the values which were 0 so that we have all the stores where sales is 0. Here we are with 0 sales. And now you can select all the sales till the end and delete them. Now we go to our sales stats sheet and start calculating the quartiles. We would like to calculate the quartile 1, or in short Q1. We would like to calculate Q2, Q3, and interquartile range, which is IQR. We only have open stores now, so we can start typing the formula in the open stores column. And we start with an equal to quartile. Here we have it. Now you need to specify the data for which you want to calculate the quartile, which is raw data, not raw data, rather clean data. And this is the column sales. And then after a semicolon, you specify, do you want to calculate the first quartile, the second quartile, the third quartile, or minimum value, maximum value. So for the first quartile, you need to specify the value 1. So we will put the value 1 and close the bracket and hit enter. So the first quartile, the 25th percentile of our sales data is coming out to be 4,865. As you can see, it is above the minimum, of course. It is below the median, and so on and so forth. Let's calculate our second quartile, which is the 50th percentile. I'll just copy this data, paste it over here, and change from 1 to 2. So this is giving us the median, and as you can see here, the value is exactly the same as the median because the second quartile represents the median. Similarly, we can copy this for the third quartile and here replace it with a 3. And here 8058 represents that 75% of our sales values lie below 8058. Now you can calculate IQR. Recall that IQR is equal to Q3 minus Q1. It's the range where we subtract Q1 from Q3. So we can do this over here. This is equal to Q3 minus Q1. And here our interquartile range is coming out to be 3,193. Now our work doesn't end here. We need to identify our lower and upper threshold, which specifies the range of our valid data points. Anything which is outside this threshold, beyond these borders, can be considered as an outlier, and that needs a special treatment. From statistics, we have the upper bound and lower bound formulas. So let's type them down. So lower bound and upper bound. Statistically, the formula for lower bound is you start with the first quartile and then you subtract 1.5 times the interquartile range. The 1.5 is a standard multiplier. If you are more conservative or less conservative, you can change the 1.5 to 2 or 1 accordingly. But 1.5 is a standard practice. So here we have 75.5 euros, which means that anything below 75 euros will be considered as an outlier. In a similar way, we can calculate the upper bound, which is an addition to Q3. So you take Q3 and then you add 1.5 times the interquartile range. And our upper bound is coming to be 12,847.5 euros. How you read this is recall that your minimum value for open stores was 612. If we now consider all the stores, then 0 is actually representing an outlier. And here it is coming out to be below 75.5, which indicates that this is lying outside our normal range. Similarly, the maximum value of 38,037, that's also an outlier because it is lying outside our maximum range of 12,847. This is actually showing that these values 0 and 38,037, these are not normal for our Rossmann sales data values. They are outliers and we need to handle them accordingly. We have another way to calculate outliers as well, and that is by visualization. Here, what you can do is go back to your cleaned data, select sales, and insert a box and whisker plot. What you get here is a graphical representation of what we have just covered. Looking closely, here you have your minimum value and here you have your maximum value. This one in the middle is your median. The lower side of the box is your first quartile or the 25th percentile. The top of the box is your 75th percentile or the third quartile. And this blue area is representing the interquartile range. And here you have all the outliers. Since we already cleaned the data, so you don't see anything in 0 and you don't see anything on the negative side of the outlier function. But here you have actually a lot of stores which have sales values above our normal range. And as you can see here, as you can imagine, these are our good performing or best performing stores which are actually worth looking at. This was a short introduction to the spread of the data, why it's important, and how it is calculated.